Hello friends, you are welcome to on my YouTube channel. In today's video, we will discuss about the applications of DC generators. Depending upon the characteristics of various type of DC generators, their important applications are given below. First, separately excited DC generators. These generators are more costly than self-excited as they require a separate source for the field excitation, but their response to the change in field resistance is more quick and precise. Therefore, these are employed where quick and definite response to control is important, such as Ward-Leonard system of speed control. When AC inductance motors were not capable, I'm talking about year 1996 and 94 in India. That time we were not having the motors, AC induction motors that can deliver the constant torque at variable speed. That time separately excited DC motors were used. This is the generator, but for reference I'm just telling you about the separately excited DC motors, and these motors were capable to deliver the constant torque at variable speed. After development in AC induction motors, the use of these DC motors were discontinued. So this is just for your knowledge only. Now let us see the shunt wound DC generator. As they provide constant terminal voltage, they are best suited for battery charging along with field regulators. They are also used for light and power supply purposes. Series bound DC generators. These generators have very few applications. Their best application is in DC locomotive, or we can say electric train system, where they supply field current for regenerative braking. They are also employed a series arc welding, arc lighting. Another application of these generators is as series booster for increasing DC voltage across the feeders. Now the compound wound generators, over compound wound type, are more suited for lighting and power services as they compensate the voltage drop in the line and the voltage at terminal of the load remains constant. Differential compound wound type are usually employed welding sets. In such cases, generator is practically short circuited every time the electrode touches the metal plates to be welded. So that were the applications, and now losses in a DC generator. While conversion of mechanical energy into electrical energy takes place, a part of energy dissipated in the form of heat surrounding air is called the losses in the generator. These losses affect the efficiency of the generator. A reduction in these losses leads to higher efficiency. Thus, major objective in the design of a DC machine is the reduction of the losses. Various losses occurring in DC machine can be divided as copper losses, iron losses, and mechanical losses. In copper losses, various windings of DC machines made of copper have some resistance. When current flows through them, there is power loss proportional to the square of their respective current. These power losses are called the copper losses. In general, various copper losses in DC machines are armature copper loss I square Ra, shunt field copper loss I square SH RSH, series field copper loss I square AC RSE, interpole winding copper loss I square Ri, brush contact loss, that is 2 IAVB, compensating winding copper loss I square R RC. The brush contact drop is generally included in armature copper loss. Now second is the iron losses. The losses which occur in iron parts of DC generator known as iron losses or core losses or magnetic losses. And in iron losses there are two type of losses. One is hysteresis, another one is eddy current. Now the power loss component as hysteresis is because of the magnetic material property, and it is expressed uh, with reasonable accuracy as pH equals to kH Vf Bm power 1.6. kH is the hysteresis constant, V is the volume of magnetic material, F is the frequency of magnetic reversal. Here the frequency of magnetic reversal is considered. Bm is the maximum flux density in the magnetic material. It occurs in the rotating machine. To minimize this loss, armature core is made of silicon steel which has low hysteresis constant. Now the eddy current loss. When flux linking with magnetic material changes or flux is cut by the magnetic material, an EMF is induced in it, which circulates eddy current through the winding, through the core. These eddy currents produce eddy current losses in the form of heat. Expressions for eddy current loss: Pe equals to Ke Vf square T square B square. K is the constant or coefficient of eddy current. T is the thickness of lamination. V is the voltage. A is the frequency, and Bm is the magnetic density. The major part of this loss occur in armature core. To minimize this loss, armature core is laminated into thin sheets from 0.3 to 0.5 mm, as in case of transformer also. Since this loss is directly proportional to the square of the thickness of lamination. Mechanical losses. As armature of a DC machine is rotating part, some power is required to overcome friction, air friction of rotating machine called windage loss, and second is friction at the bearing and friction between brushes and commutator called friction loss. These losses are known as mechanical losses. To reduce these losses, proper lubrication is done at the bearings. So these are the mechanical losses. So mechanical losses plus iron losses equals to stray losses. Now next is the efficiency of DC generator. The ratio of output power to the input power in a DC generator is called its efficiency. Now the input power equals to power output, variable losses and constant losses. Since shunt field current ISH is very small as compared to the line current, IL is approximately equal to armature current. Variable losses will become I square IL square RA, constant losses say PC, then power output will become this, and the efficiency will be VIL upon VIL plus losses. Now what is the condition for the maximum efficiency of DC generator? So as we have seen, the formula for the efficiency is this. Now the derivation with respect to differentiation of this term with respect to IL should be 0, then we will get RA upon V equals to PC upon VIL square, or you can say I square RA equals to PC. So I square RA are the variable losses and PC is the constant losses. So when variable losses will be equal to constant losses, the efficiency will be maximum. Hence the efficiency of a DC machine will be maximum when the line current in such that constant losses are equal to variable losses. And when the maximum efficiency will be maximum, from this equation we can find out the load current will be equal to under root of constant losses divided by armature resistance.